just to remind you, we sort of had this qualitative argument that if our electric field, if our potential changes a lot, then our electric field changes a lot. And then so we said, well, the electric field must be proportional to the change in the potential. And then came up with this idea that E cosine theta is the negative of dV/dS. We're getting somewhere with this, so let me show you. So where the electric field is, it comes about this E cosine theta from our F dot V, right? Because our force and our displacement have to be in the same direction. Anyway, so we came up with this expression that the electric field in a particular direction is the derivative of the potential with respect to whatever that direction is, or the negative of the derivative of that potential. And so we get this EX, EY, and EZ. I wrote them as derivatives, dV, dx, but in reality this should be the partial derivative of V with respect to X in the I direction. That's the Greek letter, what is that Greek letter actually? I don't know. Oh, it's the del. So that's del V, del X. The Greek letter is del or delta? I think it's del. Anyway, del V, del X, that's the partial derivative of V with respect to X. It's a lot like a regular derivative, except whenever you take the derivative of V here, the function V, you're taking it with respect only to X. I'll show you what that means in practice in just a minute, but it works a lot like a regular derivative. Right. And so likewise with that's our EX. Our EY is going to be negative del V del Y in the J direction, and our EZ is going to be negative del V del Z in the K direction. All right, so we use that to find the X, Y, and Z components of our electric field. So our electric field then in vector notation will just be the sum of those three. Our electric field will equal EX in the I direction plus EY in the J direction plus EZ in the K direction. Let's just do an example. I'm going to do one here, and then there's one I'll let you do on your own in just a second. So let's say that we have a potential field, V, that's going to be in terms of X, Y, and Z. And remember, potential is a scalar quantity, so there's no vectors involved here. Let's say that it's 2xy plus 3z. All right, somehow I've created this potential field. I can build it in a circuit. I can build it in the lab. You know, I have this potential that varies with x, y, and z in this way. And I want to know what is the electric field at a particular point. So what is the electric field? I don't know, let's just say at x equal 1, y equal 0, and z equal 3. What is the electric field at those points? At that particular point in space. X equal 1, y equals 0, z equals 3. In order to find the function for the electric field, I say Ex is negative del V del X. That's the partial derivative of that function with respect to X. So it's going to be negative del X of that function, which is 2xy plus 3z. When I apply this partial derivative, I take the derivative of each of these terms, but only with respect to x. So whenever I look at this function, if I'm taking the partial with respect to x, I imagine that these things are all constant. I only want to know how is the function changing with respect to x. And so if I take the derivative of this first part of the function, what is the derivative of this with respect to x? It's just going to be 2y plus what? Plus 0. Yeah, so here, if I had an x term, this is just a constant in terms of x, right? This does not change with respect to x, so the derivative of this is going to be 0. So I'm just going to have 2y is the derivative of this. So it's going to be negative 2y. So you see partial derivatives work a lot like regular derivatives. They're a little more complicated. If you ever get a chance, you can take a course in it in the math department, but they're actually quite a bit more complicated than differential equations. Y'all take differential equations? Some of the engineers in the group do. Yeah, y'all. I don't think. What's that? I think it's your last math. Is that right? Out in the math department at least. All right. So EY is negative del V del Y. That's negative del Y. 2xy plus 3z. And if I take the partial of this with respect to y, I look at this term, and I imagine that the 2 and the x are constants. And so the partial of this term alone is going to be what? 2x, yeah, because the x is also a constant. And the negative just because I have a negative there in the front. So my derivative of that is going to be negative 2x. And then finally, EZ is negative del V del Z. Again, those are Greek letters, not 2's. They sort of look like a 2, but they're Greek letters. That's negative 3. Right. I'm just taking the partial of that function with respect to z, so letting x and y be constants. And then I get an expression for my electric field. It's going to be negative 2y in the I direction minus 2x in the j direction minus 3 in the z direction. Excuse me, minus 3k. Alright, so if I want to know the electric field at a particular point, x equals 1, y equals 0, z equals 3, I let x equal 1, y equals 0, z equals 3, and then I find that the electric field is 0I minus 2j minus 3k. Just plugging in those values where they are in the function for the electric field. It's a really nice way to get back and forth between my electric potential and my electric field, where I can take that potential function, which is a scalar quantity, and pull out a vector quantity in my electric field. And it just looks at how that electric potential changes. If the electric potential changes a lot, then my electric field is going to be bigger. If it doesn't change very much, then it's going to be smaller. Let's try one on your own. Can I go down from here? All right, try this one out. There's a function v of x, y, and z. First, just find the electric field, and then we'll deal with finding the magnitude and direction of the force on that electric field. I have this function xy squared minus 3yx plus 4y. I just want to know the electric field. So you're going to be finding ex, ey, and ez. Taking the partial of each of those. the EX function for me? Negative y squared, that's right, negative y squared minus 3y, so, or plus 3y actually, right? Right, yeah, so we negate the whole thing. So it's going to be equal to negative y squared plus 3y. And that's going to be in the I direction. The y derivative, ey, negative 2xy, what was it? That's right, yeah, negative 2xy. Yeah, remember if you're taking the partial of a function that's an exponent, then that's going to be, what is it? Nx to the n minus 1. Just remind you, taking the derivatives. All right, and then for the z, what is it? 0. Right, there are no z's, so it doesn't change. This function does not change as a function of z, and so the derivative, which measures how it changes, is 0. It doesn't change at all. All right, and now we just put in our values here, x equal 1 and y equal 1, and we can get a function for our electric field. That's going to be negative 1 plus 3 in the I direction. See, I just put y equal 1 there and y equal 1 there. And then negative 2 plus 3 minus 4 in the j direction. There is no z component, so that's 2i and minus 3j. So that's my electric field. You can see a problem similar to this. I'll just give you a function, and you have to find the electric field. And then in addition to that, since we've done electric fields, oh gosh, what did our last test cover? I completely forgot. Did we just have a test in this class? We did, right? Did we do potential? Oh, yeah. Before Marty left. Yeah. So anyway, you can see this electric field stuff, and then like here there was an add-on to this question: what is the magnitude and direction of the force on the electron? That was covered on the last test, right? Yeah, so I might not have that, but yeah. So if I want to do that, if I want to know the magnitude and direction of the force, I could say F equals QE. All right, that finds the force. So that's going to be for an electron, that's negative 1.6 times 10 to the minus 19. So there'll be negative 3.2 times 10 to the minus 19. That's just 2 times the charge of an electron. In the I direction, minus what? 4.8, or be plus 4.8 times 10 to the minus 19. In the j direction, that's in newtons. And then if you want to know the magnitude of that force, it's just the square root of the x component squared plus the y component squared. I'm not going to do that here, but just taking the Pythagorean theorem on those two vectors, and then finding the angle. Of course, is the inverse tan of Fy over Fx. We've already had that on the last exam. I'll probably just give you a simpler question. Just what is the electric field? All right, that should be pretty easy, I think, right? Finding the electric field. It's really just taking a derivative. But it's a little bit different because we're doing a partial derivative where we're holding other variables as constant while we're taking the derivative with respect to another variable. All right. Well, that's the end of that chapter. So on the next test, looks like we did not have potential on the last test, correct? It just went up through electric fields. So I guess it's just all of this chapter then. Yeah, so on the next test it'll be all this information about electric potential. We're going to move now into capacitance. And I sort of find this, I like this a lot better than what we've been doing. So if you sort of found what we've been doing dry, you might like capacitors, because we're going to move a lot of the circuits now. And circuits are kind of fun. They're really sort of like puzzles that you have to pull apart and put together or whatever. The math isn't terribly complicated, and even the science isn't terribly complicated, but there's a lot of uses for it. And if you ever go into any instrumentation, which some of you might as chemistry students, it could prove useful for you in just sort of working with circuits and understanding how to interpret circuit diagrams. All right, we're going to deal with capacitors, and then we'll also deal with resistors in a later chapter, and then we'll come back and we'll deal with resistors and capacitors in the same circuits. So first of all, we'll just define what capacitance is, or capacitor. I always think of capacitors, by the way, capacitance, in my mind anyway, it is some capacity to store charge. So whenever we talk about a capacitor, we're going to talk about how much charge can it store. It has a certain capacity to store charge, because that's what a capacitor does. It stores charge and you save it for later. We're going to deal with parallel plate capacitor, which are the most common. It consists of two metal plates of area A separated by a distance d. We've talked about this actually. We sort of drawn this cartoon version of a capacitor in the previous chapter. A capacitor is just one metal plate separated from another metal plate. They have a certain area and they're separated by a distance d. Remember, we talked about these because we talked about how if you get charges on one side, positive and negative, then we set up this electric field. So within a capacitor you have this electric field. We're not going to talk about the electric field in terms of the capacitor, but we've already dealt with this cartoon version of a capacitor a lot when we're talking about electric fields. When connected to a battery, the capacitor becomes charged and stores energy that can be used later. When we talk about the charge on a capacitor, we're going to call that Q. So it stores a charge Q. We'll measure that in coulombs, just like we've done before. Although in reality, when you talk about the charge on a capacitor Q, really what you get is you get on one plate, you get a positive Q, and then on the other plate, you get a negative Q. But we'll just talk about this in terms of the total charge Q. I have a little video. This is a guy that used a capacitor to act as a battery in his car. Now, a capacitor isn't a battery, but in a lot of ways it's like that because it can take energy and store it for later. So if you hook up a capacitor to a battery like this, it will store charge on the capacitor. It will build up charge on the capacitor. And then if you take away the battery, then that charge stays on the capacitor. And it can stay for a long time. Eventually it'll sort of bleed off, but it can stay for a long time. Now in contrast, a battery, which we'll talk about in the next chapter, a battery does what to produce charge? How does it create electrical energy? There's a chemical reaction, right? We'll talk about that next chapter, but there's a chemical reaction that actually creates this electrical charge. A capacitor, there is no chemical reaction. It's that you just have physically two metal plates, they're not touching. When you apply a potential difference to them, you set up these charges on the plates, and then later you can use those charges to create an electrical current, which will also get it. Right, so this guy uses these capacitors to act as a source of electrical current for his car. It's kind of interesting. We're not going to watch the whole thing. I just want to show you the first few minutes of it. Because one of the primary purposes of capacitors is to store energy for later. Later on in this chapter, we'll see how you can also use capacitors for timing, because they respond on a very specific time interval. Let's watch this. All right, so anyway, the reason you wouldn't want to use a capacitor is because he sort of alluded to is that over time it loses the charge and it'll sort of bleed off. And he said that it lasts for a couple days, but beyond that, it might not be real reliable. Whereas a battery can last for weeks or months without charging. So anyway, the purpose of a capacitor is to store electrical charge or electrical energy. The capacitance of a capacitor is defined by the amount of charge it holds when with a certain potential difference between the plates. So you apply a certain potential difference, you see how much charge it holds, this capacitor, you can measure that charge, and then that defines what the capacitance is. Can I go down? Yes. Alright, so C then is defined as Q over V. That's our definition, how we define the capacitance. We'll describe the capacitance in a slightly different ways later based on the geometry of the capacitor. Often I'll write this not in this way, but I'll write it in terms of this, that Q is equal to CV. Right, so if my voltage goes up, that means my charge goes up for a given capacitor. If I have a certain voltage on a capacitor and then I increase that capacitance given the same voltage, I increase the amount of charge. So if I increase the capacity to store charge, then I'll increase the charge that it holds. The units of the capacitance are the farad. That's after Michael Faraday. It's capital F if you want to abbreviate it. And 1 farad is equivalent to, just based on this definition, 1 coulomb per volt. That just comes about from the definition of capacitance. And so for the previous figure, if the charge was 24 microcoulombs, for example, we had C as Q over V. If that capacitor had 24 microcoulombs, the battery was providing 12 volts, so that means the capacitance would be 2 microfarads. So a really simple way to calculate, like I said, the math isn't very difficult or simple algebra. But we'll use this relationship a lot, this whole Q equals CV. We'll use it for circuits, and then we'll also use it just sort of for basic capacitor work. Let's try this quick test. Capacitor C1 is connected across a battery of 5 volts. Identical capacitor C2 connected across a battery of 2 volts. Which capacitor has the most charge? Right, let me remind you that here Q, the amount of charge that's held on a capacitor, is equal to C times V. Now it says that C1 and C2 are identical. One of them has 5 volts and the other has 2 volts across it. So which of those has the most charge? Alright, just a few more seconds. I'll stop at 122. Okay, C1 is the right answer. If C1 has a greater voltage across it, then it's going to have more charge on it, right? Just from that relationship. If the capacitances are the same, if C is constant, then if V increases, then Q is going to be larger. All right, let's... For a parallel plate capacitor, the capacitance is dependent upon the geometric proportions, the geometry, and we only have 2 quantities that describe the dimensions. We have the distance between the plates and the area of the plates. You don't have any reason to know why the capacitance might change when those things change, but I think it's sort of intuitive. So let's try these questions. How is the amount of charge affected if the area is increased? That is, if we make those plates bigger, what happens to the amount of charge that the capacitor can hold? How is the capacity to store charge affected if you make the plates bigger, if you increase the area? Does it store more charge, less charge, or the same amount of charge? All right, doing pretty well on this. If you're not sure, ask your neighbor. Almost everybody has it. Everybody has it right, right? All right, I'll stop at 55. 55. All right, very good. Let's see how we do on the next one too. So also, if you pull those plates apart, how is the amount of charge stored? So if I, instead of having them this close, I pull them further apart, how is that going to affect the amount of charge that the capacitor can hold if I pull them further apart? All right, doing very well. Everybody has it right, so if you're not sure, just ask your neighbor. Whoop. Okay, a couple people have it wrong. But. All right, good. I'm going to stop at 37. 37. All right, good job. I don't have a good joke. Y'all want to see the pictures from our weekend?
Sure.
You care? Of course you care. Let's see. We went up to Palmetto State Park, Palmetto Island State Park. Ever been up there? It's in Abbeville, near Abbeville. It's a fairly new park. We went camping. We had a cabin. But we did a lot of geocaching and just sort of hanging out in the park. There was my boy. He had some binoculars, so he was looking at nothing. But you know what geocaching is? Where you go out, you have a GPS, and you find things that people have hidden. So we got like 7 or 8 caches while we were out. Our kids just found one. They were pillaging it, going through all the stuff they found. See, that was on the Vermilion River. Vermilion, am I saying that right? Yeah, whatever. Okay. Weather was pretty nice. It was supposed to rain all day, the full day that we were there. We were there for 2.5 days, but it didn't rain at all. See, there were lots of trails out. We tried a selfie, but it didn't work very well. Ada got cut out. Ada got cut out again. Micah tried to strangle her. So, we saw some wild hogs out on this trail. There's a bunch out there and a ton of armadillos. More geocaching. Ada got tired. Micah carried her. Sort of riding around. We went into Abbeville. Everything was closed, of course, because it was Mardi Gras, but we just sort of hung out in town. And it did rain one afternoon while we were there, so the kids built forts, and we played lots of games and stuff. So, anyway. You're welcome. All right, let's see. Okay, so the capacitance increases with area, and it's an inverse proportionality with the distance. So C is proportional to A, C is inversely proportional to D. So then we can create this expression for the capacitance, A over D, and it turns out that it's proportional to the permeativity of free space, which we've seen before. Remember, this is based on our Coulomb's constant. K was 1 over 4 pi epsilon naught. We saw that before. This is the constant. It's on your equation sheet. You'll have it. You could have a question where I just give you the geometry of a capacitor and ask you how much charge it holds, given a certain potential. All right. Let's try this one. This is a little trickier. A capacitor is hooked up to a battery with a voltage of 12 volts. After charging the capacitor, the battery is removed. What is the voltage across the capacitor if the area of the plate is doubled? And when you remove the battery, or when you charge the capacitor, it gets X amount of charge, right? when you take away the battery, that charge stays on the capacitor. And if you change the shape of the capacitor, you still have the same amount of charge. So what you want to know is then, by changing the capacitor, if the charge remains constant, how is the voltage changed? So you're looking at a couple of different relationships here. You're looking at C, which is epsilon naught A over D. And then also Q is equal to CV. So I'm changing here the area. I'm keeping Q constant, and I want to know what happens to the voltage. Oh, did I start it? Yeah. About 10 more seconds. 155. So let's see, most of you put C. If I increase the area by a factor of 2, that means I increase my capacitance by a factor of 2. If I increase the capacitance by a factor of 2, if this remains constant, my voltage has to go down by a factor of 1/2. So what did y'all put? You put C? That's right. Yeah, so it's a nice way you can change the voltage in a circuit without actually changing the electrical properties. All right. Another crucial part. Yeah, Josh.
It's a capacitor related question. In the video as well, yeah, they're circle.
Uh-huh.
Why are they in a circle if there's 2 plates?
I'll let me show you.
Oh.
It has to do with dielectrics. So it's just a matter of how they make them. Yeah, so anytime you see a capacitor, most times when you see a capacitor, they're cylindrical. They make different types of capacitors. I'll show you a video in just a sec. But they do that by using dielectrics. The dielectric is just an insulating material. They put it between the 2 plates. And it serves 2 purposes. One, it increases the capacitance of the capacitor, and then it also allows the plates to not touch. Because it's very difficult to hold 2 metal plates parallel and apart from one another without them actually touching. They actually get quite close to one another. So 2 purposes for the dielectric. It increases the capacitance. Alright, so if I have a capacitor with C naught, if I put in a dielectric, this is called the dielectric constant. It tells us by how much is the capacitance increased. I'm about to get to your question, Josh. This is the Greek letter kappa. It's always greater than 1, so it always causes the capacitance to increase, never to decrease. But also, more practical, I go down from this one, is that it allows you, it keeps the 2 plates separate, or it keeps the 2 plates from touching. Alright, so they'll take 2 metal plates, they'll be connected to some leads, and then they'll put a dielectric in between them. Usually it's like a piece of paper with wax on it or something along those lines. And then they take the whole thing and they roll it up. So you get your 2 plates like this. It sort of reminds me of the roly-poly. You remember the roly-poly that used to be in Thibodeau? They made those little wraps that weren't very good.
Oh yeah, they got one now.
Oh, do they? Yeah, so it's sort of like a roly-poly wrap. And then they have paper in between these that keeps them from touching. Keeps the 2 plates from touching.
When you say 2 plates, you don't literally mean like 2 flat pieces.
Yeah,
Like,
two metal.
It just means that they're rolled.
Right, they're rolled up in a circle. Let me show you a
Okay.
video. It shows how this guy takes them apart. This is from Magazine. Ever watch Magazine? They have a YouTube channel. They sort of talk about how things are made, and they show you different circuits to make and stuff like that. It's kind of a cool channel. But this is a video about the insides of a capacitor and what capacitors do. Let's see, I'm not sure how long it is. Yeah, I think we'll wrap up with this video, so if you want to go ahead and put your difference away, that's fine. It's about 8 minutes long. Let me go ahead